Hello everyone, welcome back to class 12 mathematics. Today we are going to answer a big question. What do we actually mean by a solution of a differential equation? Now think about your old friends, the algebraic equations. Something like x squared plus 1 equals 0. Its solution is a number. Here it would be x equals plus or minus I, an imaginary number. Or take another, x plus y equals 7. That one gives you a neat line of solutions in coordinate geometry. But differential equations? They're not looking for numbers. They're looking for functions. For example, consider the equation d squared y by dx squared plus y equals 0. Here, a solution is not a single value but an entire function y of x that makes the equation true everywhere. So the key difference is this. Algebraic equations give us points, but differential equations give us curves, entire families of them. That's why we sometimes call them solution curves or integral curves. They don't just tell us where something is. They tell us how it behaves continuously. Alright, let's talk about the general solution. By definition, a general solution contains as many arbitrary constants as the order of the differential equation. Take the equation d squared y by dx squared plus y equals 0. Its general solution is y equals a cosine x plus b sine x, where a and b are arbitrary real constants. Notice what's happening. We don't have a single curve, we have an entire family of curves. Choosing different values of a and b will give us different solution curves. Some look like stretched cosines, others look like shifted sines. In short, the general solution is like a parent family tree. It holds all the possible solutions under one umbrella, with arbitrary constants acting as dies we can turn. Now let's see how we pin down one specific member of that family. That's where the particular solution comes in. Suppose in the general solution y equals a cosine x plus b sine x, we set a equals to and b equals pi by 4. This gives us a single, very specific curve. Y equals to sine of bracket x plus pi by 4 bracket close. This curve is no longer arbitrary. It has been customized to fit initial or boundary conditions. For example, in physics, if you know the position of a particle at time 0, or in biology, the population at the start, those conditions allow us to fix A and B and get a unique solution. So remember, general solution is the whole wardrobe, but particular solution is the one outfit you pick for the occasion. Of course, we can't just guess and hope. How do we know if a function really solves a differential equation? The answer is simple. Substitute and check. Take the differential equation d squared y by dx squared plus 6dy by dx minus y equals 0. Let's test the function y equals e to the power minus 3x. Differentiate it. First derivative dy by dx equals minus 3e to the power minus 3x. Second derivative d squared y by dx squared equals 9e to the power minus 3x. Now substitute back. 9e to the power minus 3x minus 18e to the power minus 3x minus e to the power minus 3x. That simplifies to 0. Perfect. The left hand side equals the right hand side. So the function is indeed a solution. So the golden rule is, substitution is the lie detector test for solutions. If it balances identically, you've got the right answer. Let's do one more important check with trigonometric functions. The equation is d squared y by dx squared plus y equals 0. We claim that the general solution y equals a cosine x plus b sine x works. Differentiate once, dy by dx equals minus a sine x plus b cosine x. Differentiate again. D squared y by dx squared equals minus a cosine x minus b sine x. Now add y and its second derivative, bracket minus a cosine x minus b sine x bracket plus bracket a cosine x plus b sine x bracket. That equals 0 for all x, verified. This shows us that sine x and cosine x are linearly independent solutions, and their combination forms the complete general solution. It's like saying sine and cosine are the two Lego blocks, and together they build every possible solution to that equation. Now, let's work through a slightly more advanced example. We are given the differential equation dy by dx equals bracket x plus 1 bracket divided by bracket 2 minus y bracket, with the condition that y is not equal to 2. Step 1. Rearrange and separate variables. Multiply both sides. Bracket 2 minus y bracket dy equals bracket x plus 1 bracket dx. Step 2. Integrate both sides. On the left, integrate 2 minus y with respect to y. That gives 2y minus y squared by 2. On the right, integrate x plus 1 with respect to x. That gives x squared by 2 plus x plus constant c. Step 3. Combine terms and rearrange. We get x squared plus y squared plus 2x minus 4y plus constant equals 0. And as our general solution, a family of conic sections depending on the value of the constant c. If we had an initial condition like y equals 0 when x equals 1, we could plug it into fix the constant and get the particular solution. So here's the moral. General solution is wide and flexible, but initial conditions lock it down into a single, precise curve. Alright, time to wrap it all up. First, we saw that solutions of algebraic equations are numbers, but solutions of differential equations are functions. Second, we defined the general solution, a family of curves with arbitrary constants equal to the order of the equation. Third, we define the particular solution obtained when those constants are fixed by given conditions. Fourth, we practiced verifying a proposed solution by substitution, the foolproof method. Fifth, we worked through examples with trigonometric functions and with separation of variables to see general and particular solutions in action. So the essence is, the general solution is like a big family of possible answers, and a particular solution is one chosen member that fits the situation. And that's the foundation of understanding solutions of differential equations. In the next video, we'll explore formation of differential equations, where we start from a family of curves and work backwards to find the day itself. See you there.